Welcome everybody to lecture 5 of electromagnetic fields. Today we will be talking about the first or like the introduction to static electric field. In the previous lectures we talked about the vector algebra, which is a needed mathematical background for this course, is a study of electrostatic field. So to study any scientific subject, there is some essential steps. Number one is the definition of basic quantities. Number two, the definition of rules of operations. Number three, to develop the postulation about fundamental relations. So our talk will be about electromagnetic fields. So what is the meaning of field? The field is a spatial, something like related to position. Spatial is something related to position. The field is a spatial distribution of either scalar or vector quantities that is time dependent or time independent. For example, so the distribution of pressure, the distribution of weather temperature, those are fields. Like we move up or down, left or right, east or west. With this motion, we see different temperatures. So we can say that the temperature, the forecast, is a field of scalar quantity, which is the temperature. The altitude, if we are talking about a topography of an area, the altitude above the sea level is also a field of a scalar quantity. Electric and magnetic fields also are examples of vector fields. If it's time independent, it would be static fields. If it's time dependent, it would be waves, and it would be electromagnetic waves that is dependent on time, which is the topic for 304, the course in the next semester. So to start talking about the electrostatic field, we're going to start by the history. So the first thing that was related to electrostatic field was the observation of the electric force between charges. So in general, like most of the branches of science that I know about, they started by observing something, doing some experiment to understand this issue, then putting some mathematical rules to describe this relation. So the same thing happened here. Somebody, Coulomb, which is a scientist, I think in the 16th century, observed that there is some electric charge and there is a force between electric charge. So when we put two charged objects next to each other, there is a force between them. So this is the observation, he started to do experiment, how this force is affected by, or what is affecting this force. He found that the force is inversely proportional to distance, and the force is proportional to the charge itself. Then he observed the direction and put his observation into this mathematical expression, which is the Coulomb's law, or the Coulomb's law of force. The law is stating his observation that the force between two charged objects is related to the amount of charge on each of them. It's proportional to the amount of charge on each of them, and it is inversely proportional to the square of the distance between them. So K is the constant of proportionality, and the direction of force is such that if the two charges are similar, they will repel, they go out away from each other. If they are of opposite charge, they will attract to each other. To describe this relation, we have this vector AR12. So F12 is the force affecting charge 2 because of charge 1. Is the force exerted by 1. So the first is the source of force, and 2 is the object that's affected by this force. So if the two charges are the same, it will repel. So the force on Q2 will be away from 1. So it is in the direction of A R12. And if they are of opposite direction, Q1, Q2 will have a negative sign. If they are both negative, it will be plus, so it is repel. If it's two positive, it will be plus, so it's a repel. If one is positive, one is negative, there will be a negative sign, and the force will be attraction. So this writing here is the observation, and this law here is the description for this observation in a mathematical model or mathematical format. Then, after the description of the force between two charges, it came the idea of electric field. So the idea here is that if I have a charge, so this charge creates a field around it, and we want to describe the field. Field is sort of like a region of effect, or a region of impact, or an area where it shows effect. So we want to describe this like effect, and they came up with this definition. So the force per unit charge, that is a very small, so that it's localized at one single point. Stationary, it is not moving. Positive unit charge, so it's 1. So that this law here, Q2 will be plus 1. So now the field will be just related to Q1, and this is the definition of, the force will be just related to Q1. If we put a test charge Q2 equal 1, positive 1 unit charge that is positive, then the force would be like related to Q1, and this is called the electric field, or the domain of effect of this charge. So electric field, the definition is the force divided by Q2 when Q2 is very small, and its units is Newton per coulomb or volt per meter. Force equal QE. It's in Newton. Those are the postulates, or the mathematical model for electrostatic, or the main rules that are describing the electric field. Then we have like this description that we're gonna, like this law also, or postulate. It is coming from observation, and we're gonna talk about in details like very soon. It is stating that the divergence of E equal rho divided by epsilon naught. In free space, divergence of this electric field equal rho, which is the volumetric charge density. Unit here is coulomb per meter cubed divided by epsilon naught, which is a constant that we're gonna just remember its value. Then also we have this postulate, or this law, which is curl of E, the curl of electric field equals 0, and we're going to talk about the physical meaning of those two postulates shortly. Okay, so now coming to like this postulate or this law. So if we just write this expression, and we take the volumetric integration of both sides over any volume. So we choose any volume, and we take the volumetric integration of both sides. Nothing had changed. Epsilon naught is a constant, so it goes out of the integration. Rho dV, so rho is the volumetric charge density, integrating volumetric charge density dV over any volume. So logically, physically, this is the total charge enclosed in this volume. Now coming to this left side of the equation, and before we move forward, let us recall the divergence theorem. Divergence theorem that we studied in previous lecture is stating that the integration of any vector A over a closed surface ds equal the divergence of A, which is a scalar quantity, d volume over the volume enclosed by this closed surface. So we have a volume here, so any volume must be enclosed by a surface. So here, this is the integration over a volume from here. So divergence of E d volume from divergence theorem, this is equivalent to the integration of E over the surface enclosing this volume. So just replacing the right hand side here with its equivalent part of the divergence theorem, and we have this law. So this law is saying that the flux of electric field out of any closed surface equal to the total charge enclosed inside the volume or enclosed inside this surface divided by a constant. Okay, so and we're going to use this in solving or in studying problems of electrostatic. So this law is called Gauss's law. Gauss is a scientist who discovered or formulated this law, and the law is stating that total net out flux electric field, we said flux is E dot ds out of a closed surface over any closed surface S in free space, and this is related to this constant, and we're going to talk about this constant later on during this course. This equals to the total charge enclosed in the volume V bounded by the surface divided by epsilon naught. So this is Gauss's law. It's a very important and fundamental law in the electrostatic. So the flux of electric field out of any closed surface equals the total charge enclosed by this surface, or the total charge in the volume enclosed by this surface divided by the constant epsilon naught. Going to the second or the other postulate or the other law, that curl of E equals 0. So before we move forward, I would like to recall the Stokes theorem that's saying that curl of a vector dot ds, where S is an open surface, equal the integration of this vector dot dl around the contour enclosing this open surface according to the right hand side. So if we have a contour like C, the contour C will enclose an open surface S. If we are integrating a vector along the contour, the closed contour, this is equivalent, or this equal to, the integration of the curl of this vector over the surface, the open surface enclosed by this contour according to the right hand side. So where is the right hand side affects us if we are rotating in that direction. So we just make the fingers of our right hand goes with the direction. Our thumb will be pointing to the side that we are talking about. Here, according to this graph, we are talking about the top side. If we are rotating in the opposite side, so we are talking about the bottom side of this surface. So back to our postulate or law. The law is saying curl of E equals 0. So applying the Stokes theorem, curl of E dot ds. So we know we take this part dot ds enclosing any open surface. This is equal to E dot dl over the closed contour surrounding this open surface. So what is the meaning of this? The physical meaning is that the line integral of E around any closed path equals 0. So what is E dot dl? E dot dl is the potential difference between 2 points. If we are integrating over a closed contour, it means that the potential difference between the start and the end of this contour, which is, because it's closed, it's the potential difference between the point and itself. So the potential difference between any point and itself equals 0. It looks trivial, but this is a major law. Why? Because it is stating that this field is conservative. And before we talk about what is the conservative field, so what is this kind of law here is very equivalent to the Kirchhoff's voltage law in circuit theory, where we studied this. We are saying that the sum of voltage drop across any closed circuit equals 0. So this is the same. The voltage drop across any closed path equals 0. So the potential difference between any point and itself, when I rotate and return back to itself, equals 0. What is the value of this? The value is that the potential of a point is like a single valued function. So we can say any point does have like a unique voltage, a unique potential, electric potential. So the point can't have two electric potential. Okay, why it's important, why it's significant, we're going to see this across our course. And this is like the case with many different things. When a field does have this property, we are saying this field is conservative. Like a very famous example of conservative field is the field of gravity of Earth and the potential energy. So we're saying any point, any object at any point does have a fixed value, a single value of potential energy that depends on how far or like how high it is from the sea level. So if you are in the entrance of the building, you are on ground zero, so you have zero potential. If you want to go for first floor, you must do effort. And this effort, like you exert work and you gain energy. So if you are carrying a ball and you lift the ball will go down because it has a potential energy, and this potential energy depends on a single value, which is the height from the sea level. If you go by elevator, if you go like from the first stair, you go from like the second stair, it doesn't matter how you reach the point on the first floor. So the path is not important. What is important is the starting point and the end point, and this kind of field is called conservative field. The potential difference between 2 points depends on their position, not depending on the path that you take from single point to the other, similar to the potential energy. It doesn't matter how did you reach like from first floor to second floor or from zero entrance to the first floor. You can go from the window, you can go by like elevator, you can go by ascensor, you can like your friend can like pull you with a rope or something. It doesn't matter. All the ways when you are on the first floor, you have a single value for your potential energy. Same thing here in electric field. The potential difference between 2 points depends on their geometry or their positions. It's not dependent on the path you take to find the potential difference. So E dot dl from between any 2 points is a constant value irrespective of the path. This is the meaning of conservative field. Now let us talk about the electric field, and we are going to study this like in incremental ways. We start with a very simple setup, then we have like a little bit more difficult or complex to reach at the end like the general setup, which can cover any kind of like configuration. So what is the source of electric field? The source of electric field, as we said earlier in the introduction, is a stationary charge. So the most simpler problem is the problem of a single point charge, and we put it in the easiest position at the origin. And we want to study the electric field associated with this point charge. So we have a point charge Q, and we locate it at the origin and would like to find the electric field associated with this charge. So the first thing here is that the field associated with a point charge at the origin must be symmetric. Why? So the idea here, like any physical problem, it's not just electrostatic. If the geometry is symmetric, the geometry does have two aspects here: the source and the observation. So in our case, the source is a point. You can consider a point as a tiny small sphere at the origin, and the observation is another point. So what should affect the field? Can the angle affect the field? So we have like three aspects here: phi, theta, and r. So from just the geometry, without understanding anything about electric field, we must reach the point that the field must depend only on r. Why? So if this point is moving on this circle here, there shouldn't be any difference, because from any point, what I see is that I see from any observation point, I just see something at the origin that is r away from my point. So there must be symmetry. If you have like a source of heat, and this source of heat is a very tiny small, and I ask you, where is the direction that receives the maximum amount of heat? Up, down, left, right, front, back? Your answer should be all the directions will get the same amount of heat, because the source is a tiny small sphere, and the environment around this tiny small sphere is all air, so it should be like distributing its output symmetrically in all directions. If we have like a source of light that is a point, and it is emitting light, and I ask you, where is the direction of the maximum amount of light intensity? You should say, okay, in all directions they are the same, because the source is a sphere emitting in all directions, and the environment around the sphere is the same, so it should direct its energy in all directions equally, which is symmetry. So there is no physical meaning from the geometry of the source. There is no physical, because the source here is a point, very tiny small sphere. There is no reason to prefer certain direction over the other, or certain angle over the other. So we would expect that this point charge emit electric field, or just create electric field uniformly or symmetrically in all directions. So if the electric field is symmetry because of the physics of the problem, because of the geometry of the problem, how can we find the value of this electric field? Now we're gonna call Gauss's law. So Gauss's law is stating that E dot ds over any closed surface equals the total charge enclosed by this surface divided by epsilon naught. And now, because of symmetry, I need to choose the closed surface to benefit from this symmetry. So I choose the surface to be a sphere with the center at the origin. So on this sphere, the electric field at any point on the sphere is the same. Why? Because it is symmetry. Because of the symmetry of the source, which is a point charge. So the electric field either going out or going in. It can't be, for example, going like left to right. It must be going again in the radial direction because of the symmetry. There is no reason to prefer certain direction over the other. Because of this symmetry, we know the electric field would be like in this direction, AR or negative AR. So E dot ds, E is in the direction of AR, ds, of course, on the surface of a sphere is in the direction of AR. So E dot ds equal the electric field multiplied by the area of the sphere. So the electric field multiplied by the area of the sphere equal Q divided by epsilon naught. So E will equal Q, this is the total charge enclosed by the surface, equal A in the direction AR divided by 4 by epsilon naught R square. 4 by R square is the surface of the sphere, and the right hand side equals the total charge divided by epsilon naught, and the direction from symmetry must be in the direction of AR. So for a point charge at the origin, we have the expression for the electric field associated with this charge. One important thing here that we're going to revisit more and more is that if I choose my surface to be a cube, and this charge is at the center of the cube, Gauss's law will be valid. E dot ds over the surface of this cube, the 6 faces of this cube, E dot ds over those 6 surfaces equal Q over epsilon naught. This is true, but it's not useful. Why? Because on the surface of those 6 faces of the cube, electric field is not constant. There is no symmetry for the electric field. So we know the Gauss's law is valid because it's a law, but we can't benefit from it. We must choose the surface to benefit from the symmetry of the problem. Otherwise, okay, the total flux out of this surface equals the total charge enclosed, but we can, if we choose the surface in a wrong way or in a way that is not benefiting from the symmetry, we can't use Gauss's law to solve the problem, and we're going to revisit this more and more. The important point here is that Gauss's law is always valid, but it is not always useful. For example, here it's useful if we choose the surface to be a sphere, but it is not useful if we choose the surface to be like a cube. In both cases, it is right. So hopefully it is clear what is the meaning. It is always correct, it's always valid, but it is not always useful. Okay, so the simplest problem setup is a point charge at the origin. Now we want to study the case of a point charge that is not at the origin, in an arbitrary position. So the point charge would be at R prime. We have Q, and we want to find the electric field at any arbitrary point B. So this is the problem. We have a point charge at any arbitrary point, and we want to find the electric field at another arbitrary point. So how would we solve this problem? Okay, so we can draw a sphere around the point charge, and we know that the electric field on any point on this sphere, we know the value and we know the direction. The direction is from point Q to point B, and the value is q over 4 pi epsilon naught multiplied by the distance between the two charges square. So this is what we learned from the previous case. So we know that at any point here, the electric field at any point is in the direction from the electric charge to the position of the observation point. So the electric field is in that direction. Its value equal q divided by 4 pi epsilon, the distance square, the distance between the point charge and the observation point. So the electric field at any point, because of a point charge at an arbitrary location, is in the direction from the point charge to the observation point. The value equal the point charge divided by 4 pi epsilon naught, the distance square. Okay, so how can we find this distance square in an arbitrary way? We can like express this vector here to equal r, the position vector to the observation point, minus the position vector to the charge. So from this point to this point, from the vector algebra, it equals this vector plus this vector. So the vector of interest to us, AQB, this vector here, equal that vector, which is minus r prime plus r. R prime is the position vector of the point charge, and the source always we put prime to the description of sources. So r prime is the position vector of the point charge. R is the position vector of the observation point. So the vector, the direction of the vector of the electric field AQB equal the vector divided by its magnitude. So it's equal r minus r prime, the position vector to the observation point, minus the position vector to the source, divided by its magnitude. This is AQB. So if we just added this, or like substituted AQB into this expression, we would have the electric field because of a point charge at any arbitrary position, observed at any arbitrary position, equal Q multiplied by the vector of the position vector of the observation minus the position vector of the source, divided by 4 pi epsilon cube, so square from where we get this expression, and the third one is coming from here. So the cube of the magnitude of position vector of observation minus the position vector of source. So those are two equivalent. They are like the expression for the electric field at an observation point, arbitrary observation point, because of a point charge located at an arbitrary position. So now let us have this example. The example is asking us, okay, determine the electric field intensity at a point P, so it's giving us an observation point, due to a point charge 5 nanocoulomb at this position. So we have a source at this position, and we have an observation at that position. At the source, we have this amount of point charge, and we need to find the electric field at this point. So this is like a very direct application for what we just learned in this slide here. So the solution would be to apply this rule. It's very straightforward. So you need to write down this. So the law that we have, this is the law here. Electric field at an observation point equal 1 over 4 pi epsilon naught multiplied by the source amount of charge Q multiplied by observation point position vector minus source point position vector as vectors divided by observation point position vector minus source point position vector magnitude cubed. So we need to find R, we need to find R prime. So R is OB from O to the point B, and it is given here. So it's minus 0.2 in X, minus 2.3 in Z. So this is the position vector of observation point. The position vector of the point charge is OQ. It is given here, 0.2 X plus 0.1 Y minus 2.5 Z. So R prime 0.2 X AX 0.1 AY minus 2.5 AZ. The difference R minus R prime, just subtract two vectors and we need to find the magnitude. So the electric field at the observation point equal 1 over 4 by epsilon naught multiplied by Q. Q is 9 nanometer divided by 4 by epsilon 1 over 4 by epsilon naught equals this value here, and this is R minus R prime divided by the magnitude cubed, so it does have this expression. Okay, this is the simplest case is a point charge at the origin. The next step is a point charge at an arbitrary location. Okay, as I said, we're gonna just try to make it as general as possible, so we keep adding more complication into the scenes that we are trying to model. And now, okay, what if we have multiple point charges? We have 5, we have 3, we have 2, whatever the number of point charges we have. Okay, we need to find the electric field at a single observation point. Okay, if we have multiple point charges, the electric field is the superposition of the electric field from every single point charge. So if I have n point charges and have any arbitrary single observation point, the electric field at this point will equal the electric field caused by charge 1 plus, and plus here means vectorial summation of the electric field caused by charge 2 plus the electric field caused by charge 3, so on and so forth till we add the electric field caused by charge n. So this is the expression for the total electric field at an observation point that has a position vector r because of n charges. Each charge at a certain position is equal the contribution from charge k equal qk r minus r prime k, the position vector of charge k divided by the magnitude cubed. So again, it's just like a direct application of what we learned. So there is like a sort of like a very famous problem, which is the problem of electric dipole. Later on the course, we'll see the value of this problem. So the problem here is that we have like 2 point charges that are equal in magnitude and opposite in sign. So if we have like point charge q and another point charge minus q, and we would like to find the electric field because of this dipole. Later on we'll see the values. There is like many usage for the electric field associated by electric dipole. and we would like to find the observation far from the dipole. Far from the dipole means that the observation point is at a distance much larger than the separation between the 2 points. So we want to find the electric field at a point where r, the distance, is much larger than the separation of the 2 charges. Okay, for like solving this problem, we're gonna put this dipole with its center at the origin and place it along the z-axis. So we have the negative charge at minus d over 2. D is the separation between the 2 charges, and the positive charge at z equal d over 2. So now the dipole is along the z-axis, and it is centered. The center is at the origin. We would like to find the electric field at an observation point, arbitrary observation point P, that have a distance from origin much larger than the separation between the 2 charges. So this is the required, and these are the given information. So we're going to apply what we just learned. If we have multiple point charges, the electric field at any point equal the electric field because of first charge plus the electric field because of the second charge. Okay, the electric field equal this summation. We have just 2 charges, so we'll have like Q also is constant, because like the positive charge and negative charge does have the same magnitude with negative with just opposite sign. R is the arbitrary observation point. R prime 1 is the position of the first charge. R prime 2 is the position of second charge. So let us apply. R is the arbitrary observation point, minus R prime is the position of the first charge. Let me write that. Okay, so I just added some details. So what we need the position vector to the observation point. We need the position vector to each charge. So the position vector to the arbitrary observation point is just R. The position vector to the positive charge is 0.5 d, where d equal like d in the AZ. So positive charge position vector equal 0.5 d. The position vector for the negative charge equal minus 0.5 d, which is in that direction. So just substituting these 2 position vector into the expression, we'll have that. Negative charge does have negative. R minus R prime for negative charge is R plus 0.5 d. R minus R prime for positive charge equal R minus 0.5 d, and negative charge is negative. So this is the expression. Now let us take this one. So this one, like what is the magnitude? As we said earlier, if we want to find the magnitude of a vector, we just take the square root of its dot product with itself. So the dot product of this vector with itself equal double the magnitude, and we need just the magnitude squared. So it would be magnitude squared divided by 2. It is in the denominator, so it has a negative sign. So writing this down, it would be R squared. R here is not a vector, is the distance between the origin and the observation point, minus twice R dot 0.5 d, which is, because we have twice, so the 0.5 will go, R dot d, and the last one is 0.25 d square, all to the minus 3 square, 3 over 2. we take the r out, r square out of this like expression, and we of course apply the power of minus 3 over 2 to it. We'll have r to the power minus 3 multiplied by 1 minus this expression divided by r square plus this value divided by r square. So we said that the r is much larger than d. So d over r is a small quantity. D over r square is a very small quantity, and we can neglect that. So this is a very valid approximation. So let us do that. So this is, let us do this. So this one is sort of like ignored because it's very small. Okay. So we are left up with, let me bring the pointer again. We are left up with this expression, and we can apply Taylor expansion. So we're going to use it frequently in electromagnetics. So just go and see the value for, or like the expression for this. The Taylor expansion of 1 minus r dot d over r square. So r dot d is equal to r d cosine the angle between them divided by r square. R will go with r, so it would be d cosine angle divided by r. Anyway, just taking the first term of Taylor expansion will give us this expression here. So we can say that the denominator here approximately equals this expression. So multiply like this value. So this is the expression for this denominator, and for the other term, the only difference, instead of minus we have plus, so we'll have similar expression with just the difference of the sign here. So the electric field now, if we want to like write this expression again after this approximation, it will have this expression here. Q over 4 pi epsilon naught is common. Now r to the minus 3 is common, it would be here. Then we have this term multiplied by this term minus this term multiplied by this term. So okay, so we'll have r, but there is a negative, so the r will cancel. Then what is left is this term with that term. Anyway, we just do the math, we'll get this expression of E for the electric dipole equal the charge of electric dipole divided by 4 pi epsilon naught r cubed. R is the distance between origin, the center of the dipole, to the observation point, multiplied by 3, this expression minus d. So this is what we have so far. So this is what we have so far. This vector here, q multiplied by d, is called the polarization vector. Q is the charge of the dipole. One point charge is q, the second point charge is minus q. So q is the dipole charge. D is the separation between the two charges. Its direction is from the negative charge to the positive charge. So this is D, the polarization vector. So the electric field, I'm going to just rewrite this expression here like D equal, so we'll take the Q inside. So Q multiplied by D equal B. Q multiplied by D equal B. So this is the expression R dot B. B is the polarization vector divided by R square multiplied by the vector R, the position vector to the observation point, minus B. So this is the general expression for the electric field generated or caused by an electric dipole. If the dipole is along the z-axis, so AZ equal AR cosine theta minus A theta sine theta. So this is like the AZ decomposed into the unit vectors of the spherical coordinate system. Of course, AZ doesn't have any component in the XY plane, so it doesn't have a component in the phi direction. It just have a component into R direction, which is cosine theta. By definition, you should be able to get this easily. So R dot B, R is in the direction of AR. This is the definition of position vector in a spherical coordinate system. So R dot B, B is in the AZ, R dot B will equal R B cosine theta. And we have here R dot B equal R B cosine theta. So the expression here, 3 R dot B in the R direction divided by R square will equal 3 R. So 1 R will go with the square, 1 R will go with this, and we are left with AR. Okay, so the dot product here, if we do this part here, it would be AR 3B, the polarization vector, the magnitude, which is QD cosine theta. Theta here is the angle of the observation point, minus B. We know B in the AZ direction, so just do the math. You don't need to memorize this, but you must be able to reproduce this result yourself. So like the electric field for a polarization electric dipole does have this expression here. It has a component in AR and a component in A theta, and this is the expression. This expression, as I said, like you don't need to memorize, but it's very important that you are able to like redo this calculation and come up with this expression yourself. This approximation here is very important. You need to review Taylor series and or like Taylor expansion and be able to like do it yourself. We're going to use this frequently in our course or like in electromagnetics in general. Like this formulation, how to express B, like how to decompose AZ into the unit vectors of cylindrical coordinate system, spherical coordinate system. All of these skills should have been learned from the first 3 lectures about vector algebra. So far, what we learned from this, we learned the fundamental postulates of electrostatic field in free space. Later on, we'll learn about different media, like Coulomb's law, Gauss's law, the conservation of electric field. We learned how to calculate the field due to discrete charges like discrete point charge. We use the superposition. We applied this on the electric dipole. So in general, like when you reach to this point, you need to like make sure that you learned what is written here. Thanks everybody, and meet you in the discussion session.